Hello. We're going to go through the do now question from the slides and question 3 and 4 from the activity in your textbook, just to have some worked answers on a video that you can refer to. So, get rid of that. The do now to start. All right. There are two ways to do it. We can read off the diagram, or we can do a calculation. All right. So we're going to just recall to ourselves we have two equations to work with here. We have for antinodes, we have path difference equals n lambda, okay? And for nodes, we have path difference equals n minus 1/2 in brackets lambda, okay? And we're going to try and maybe use those equations here. And we'll just recall to ourselves as well, an antinode would be a bright, if it's light, spot, or it would be loud if it was sound. Okay, and a point of no displacement, a node will be dark or quiet. Okay, so let's go ahead and try and do both methods while we're here. We will do diagram method on the left. And then on the right, we'll do some calculations. So, A, B, and C, and D, and E. A, B, C, D, and E. Okay, A. What we want to do is we want to count the number of wavelengths out from S1 and S2. All right, so we're going to go 1 wavelength, 2 and 3 wavelengths, and 1, 2, 3 and a half wavelengths. Okay, equals PD equals 1/2 lambda. So if the path difference is half of a wavelength, we're probably looking at a node. Because antinodes have a path difference of n, one whole integer of a wavelength. If we're looking at fractions of a wavelength in halves, then we should be looking at a node. Okay, let's do B next. We're going to go 1 wavelength, 2 wavelengths out from S1, 1, 2 and a half from S2. So again, PD equals 1/2 lambda, so it's a node as well. And we can see that because it's lying on one peak and it's in the middle from S2, which means it's in a trough there, so a peak and a trough are meeting. C. Let's do C. Count out from S1. 1, 2, 3, 4. 1, 2, 3. Cool, so the difference between 3 and 4 is 1. So our path difference equals 1 wavelength, so it's an antinode. And we can see that we're getting a peak and a peak. Okay, that's cool. D. 1, 2, 3, 4 out. It's a bit of a terrible line, and 1. So the difference, PD, 4 and 3, so it's 4 and 1, so it's 3 wavelengths. So it's an antinode. Because our difference is 3 wavelengths. And E, we'll go 1, 2, 3.5, and 1, 2.5. 2.5 and 3.5, the difference is 1 wavelength. So it's an antinode. Okay, you guys with me so far? Just checking we're recording. Awesome. All right, so that's the reading of the diagram version. Okay, and we can do a calculations version as well, which also works quite well. So let's try that, shall we? For A, we're just going to look at the diagram and we're going to say it's lying on a peak and a trough, so it's going to be a node. Therefore, or 3 dots, we're going to use PD equals n minus a half lambda. And what's our n? For A, n, we've got a bright line up the middle. This is n equals, that's bright spot 0. Then we've got a dark line in here. Then we've got another node line. Okay, so that's a nodal line. It's a bit unclear, but let's see if we can write this. N equals 1, m equals 1, n equals 2, m equals 1, n equals 2, where n is an antinode and m is a node. Okay, so it's a bit hard to do the calculations of the lines drawn on a diagram, but we'll kind of see if we can battle on through. Okay, so we're going to know that A is on 1, so P equals 1 minus a half times our wavelength equals 1/2 lambda, and that matches our previous one, so that's really nice. Okay, B we think is a node as well, therefore we're going to use PD again equals n minus a half lambda. So let's have a look. B here appears to be on the same line as A, so it's going to be 1 again. 1 minus 1/2 lambda equals 1/2 lambda, and that matches what we saw earlier, which is awesome. C, we think C is an antinode because it lies up here on the intersection of 2 peaks. Okay, so antinode. Therefore, PD equals m lambda, because we're looking at an antinode, and we think C is on our second antinodal line. Okay, PD, so n equals 2, 2 minus, oh, goodness, did we count that one wrong? 1, 2, 3, 4 out to C, 1, 2, 3 out to C. Oops, I made a mistake. The center line is called, how do I make it smaller? There we go. The center line is n equals 0. 0. There we go. That's my bad. 1, 1. Okay, I think we have a 0th line in the middle. Good. So now I'm not losing my mind. Our maths works. We're on n equals 1. And we've got, yeah, so we've got 1 lambda, which is great. D is an antinode. Oops. Therefore, PD equals, which n are we on for D? We're going to have a look over here. D is going to be something way out on the side. It's really quite hard to tell. If we kept drawing little dotted lines, we're going to get one there, then we're going to have one that's going to come through the middle, and then through the next set of peaks, intersections, and then through the middle, and then through the next set of peaks. Okay, and we're going to go m equals 1, m equals 2, n equals 2, m equals 3, n equals 3. Okay, so we think D is probably on 3. and it's going to be 3 lambda. E, antinode as well. So path difference should be, for E, we think it's on n equals 1, so 1 lambda. Okay. So the calculations is a bit harder there because the diagram wasn't set up for calculations, but we can kind of infer it as well. Okay, let's continue on down. Have a look at some textbook questions here. I thought we could do 3 and 4. Finn just pointed out that I put on your document to do 4 and 5, but question 5 does not exist in this chapter. So you would have had a hard time doing question 5 from this chapter, but that's okay. So we'll do 3 and 4. Okay, let's do, I think, 4 first, because I think it's easier to do 4, and then we'll go back and do 3, because it's got a slightly more complicated question in it. Okay, so let's look at number 4. Let's have a quick read. An interference pattern is produced by green monochromatic light. Okay, that's cool. Passing through slits 0.02 centimeters apart. Okay, so that's our first piece of information. Now, if we remember our formula, write it here, shall I? PD equals dx over L. We've got, yeah, we'll leave that one there for now. The slit separation is known as D. Okay, so what we're going to try and do is we're going to turn the centimeters into meters, and we're going to say D equals, I think it will be 0 point a lot. I think it's 3 zeros. 0, 0, 0, 2 meters. Okay, so that's the first thing we've noticed. The light's passing through the slit and projected onto a screen 1.2 meters away. So if we know how far away something is, it'll be L, 1.2 meters. And now the next tricky thing is that they've said they've counted 10 intervals, or 11 bright fringes over 3 centimeters on the screen. Okay, so what we're going to have to do now is draw a bit of a diagram and see if we can figure out X. Okay, just remembering our end goal is calculate frequency. Okay, F is unknown, but we know that we're going to need X because we need to use this. We need to use this equation, but we don't have X yet. So let's draw a little diagram. It's going to be wildly not to scale, but that's okay. We're going to have on our left-hand side a barrier with 2 slits. Okay, so that the light can come through it. That's cool. And on the right-hand side, all the way over here, we're going to have a nice big screen as well. Okay, somewhere in the middle here, we'll just make a couple of notations. The distance between these 2 slits here, D equals 0.0002 meters. Okay, and the other thing for us to note is that the distance here between source and screen, L equals 1.2 meters. Okay, those are the things we know so far. Now, they're telling us we have 11 bright fringes. So we'll count from the center. We've got bright fringe in the center 1, the 0. Then we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, that will work. So we've got our center 1, and we've got 10 more fringes out to the side. Okay, and they tell us that the distance between the middle and here, we're counting 11 bright fringes over 3 centimeters. Okay, over 3 centimeters. So what I want to ask you guys is how far between each fringe? That's what we need to think about, because we know the total distance over 11 fringes, but we need to know what's the actual separation between two fringes. Okay, and we should be able to see that the separation between any two fringes, x equals 0.3 centimeters. Okay, because we have 10 gaps. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intervals. Okay, 10 spaces. So we divide 3 centimeters by 10, and we know each fringe is 0.3 centimeters apart, which we have to give in meters. Okay, which is 0, come on, 0.003 meters. Okay, 0.3, so it's 3 millimeters. Okay, so that's great. We have enough information to work out, to use our equation over here. But let's just think before we do a calculation. We want to find frequency, yes? This is our end goal. This is how we actually get some marks in this question. Okay, how do we figure out frequency? It's certainly not from this equation. Frequency is not given here. Okay, so we need a way to work out frequency. The best way to work out frequency, I think, would be to use V equals F lambda. V, oops, not the eraser. V equals F lambda. Okay, where F equals V divided by lambda. That's great. So we're going to use this equation to find frequency. Find F. Okay, but the problem is we don't know wavelength. We don't know lambda yet. Okay, how are we going to find lambda? We're going to find lambda by using this equation from before, using our nodal antinodal path difference equations. Okay, now we know that we're looking at bright spots, so we're looking at antinodes. PD equals m lambda. So PD equals n lambda. Lambda equals PD divided by n. Great. We can choose any fringe we want, so we can choose any n we want. That's good. What we need to know is we don't know the path difference. PD. We need to find PD is unknown. Okay, how are we going to find PD? We're going to use our path difference equation from the top. Okay, so let's go ahead and do that. When my pen's not working properly. Just want to select blue as a color. Come on. Fine, I'll do it in green. Oh, there it goes. Okay, so PD equals dx over L. Okay, D, the separation of the two sources, 0.1232 meters times by x, the separation of the fringes, 0.1233. Okay. What did I do here? 0.00. Whoops, I think this one here, x, I made a little typo earlier, freaking you all out, I think. Should be, yeah, 0.3 centimeters. Yeah, I've just made a transcription error. There we go, we're all good. I just can't read what I wrote earlier. This value up here, 0.003. There we go, nice. And we've got to divide it by the distance, L, between source and plate, 1.2. Okay, and I worked this out earlier. No, I didn't. That was very useful. 0.0002. 5 times 10 to the negative 7 meters. Okay, hopefully I haven't made a mathematical error, and you guys will agree. Okay, so what we've done here is we've figured out the path difference. How much further one wave has to travel than the other. Okay, so we've figured out path difference. So what we're going to do is we're going to take this value here and we're going to start working backwards. Okay, we're going to take it and we're going to put it up over here in this equation. Okay, lambda equals 5 times 10 to the negative 7 divided by n. Now we can do any fringe we like, so I think we're going to do n equals 1. Okay. Therefore, our lambda is actually 5 times 10 to the 7, negative 7 meters. Okay. So that's our wavelength. And we're going to take this value here, and we're going to go back another step. Okay. Up over into here. Oops. And we're going to say F equals, we know it's light, so 3 times 10 to the 8 divided by 5 times 10 to the negative 7. Okay. Oh, 6 times 10 to the 14 hertz. Okay, where this here is our final answer. This is our frequency. All right, hopefully I didn't do any maths errors, but it's just good to see the process. All right, so we know we wanted frequency. We're going to use our wave equation for equals left lambda. We don't know lambda, so how we're going to find that? Probably use our path difference equation. Okay, P equals m lambda because it's a bright part, so we want to use the antinode version. And then we don't know path difference, so we're going to use our path difference equation, P equals dx over L, to find that and start working backwards, placing things in. Okay, so that was 4a. Calculate the frequency. All right, and here it asks what's the fundamental frequency. I gave my answer in as hertz. Okay, but we know hertz actually equals per second, s times s to the minus 1. Okay, that's our fundamental unit. Now, B is where it gets really exciting. Okay, for B, what if blue instead of green? Okay, what if blue, not green? Okay, impact, oops, that's not how capital I's work. Impact they want to know, how does this change the fringe pattern on X? This is our fringe pattern. Okay, fringe separation. We want to know what's the impact on X. Okay, now we have to think first, okay, so if we take our wave equation, PD equals dx over L, we want to rearrange this so I can see X by itself. Okay, P D times L over D equals X. Okay, that's fine. We can see how X will change when we change these variables. All right, if PD gets bigger, the fringe separation gets bigger. If the distance between the source and the screen, the L, gets bigger, the fringe separation X gets bigger. If distance between D, between our two things up over here, if they get bigger, if D, our denominator, gets bigger, we know that the fringe separation is going to get smaller because we're dividing by a bigger number. Okay, that's all great, but we haven't thought about wavelength yet. Okay, now let's think about our rainbow. Roy G. Biv. G. Biv. Okay, what if blue, not green? So currently we're here, G, and we want to go to B. Okay, we want to go to B. All right. Now, how does the wavelength change between G and B? We know that red is the longest down here, longest lambda, shortest lambda. Okay, so we know the wavelength is going down. Okay, blue, not green. So lambda is decreasing. Wavelength is decreasing. Okay, that's good. That's a step in the right direction. But we need to know about how this actually impacts x. And we're going to do that by thinking about how lambda decreasing impacts PD equals n lambda. Okay? If lambda goes down, path difference goes down. Why? Because n is constant. The first fringe is always the first fringe. N is always equals 1. And the second fringe is always the second fringe. So n always equals 2. The n doesn't necessarily change. It has to be constant. Okay? So if lambda goes down, path difference goes down. Okay? Great. Lambda is decreasing. PD decreases. Okay? And then if we think about this equation up over here, if PD decreases, what happens to x? X decreases. There we go. Fringes get closer together. That's what that means. Okay? That's what that means. All right. So that's question 4 from your textbook. What we should try and do is think about question 3 as well, a bit briefly while we're here. All right, so we'll make a copy of this, I think. Yep. Can I paste it? Is that how that works? How do I paste? There we go. Okay. So we just did that. And now we're going to do 3. All right. So, question 3. 2 point systems of a wave are 0.1 mil apart. Okay, so we're reading our question again. D, our source separation, 1 mil, 0.001 meters. A distance of 1 meter away, L equals 1 meter. Apologies, I just had to sneeze. And we know the distance between the third nodal lines either side of the central antinodal line is 3.2 millimeters. Okay. Now, what we should try and do is draw a diagram. All right. Again, on our left-hand side, we're going to have two sources. They can be little boxes or they can be slits and a barrier. That's fine. And then on our right-hand side, we're going to have our screen. Okay, just like before. All right, just the recording cut out, so we'll just continue on from there. What we need to do is think about our diagram here to help us understand this last part about our distance between the third nodal lines either side of the central antinodal line is 3.2 millimeters. All right, so we know in the middle here, we're going to have bright. We know that's how that works, okay? Bright. And then we're going to go dark, then it's going to go bright again, then dark, then bright, and then dark, and continue on, okay, and bright. It happens the same in the other direction. Bright, and then dark, and then bright, and then dark, bright, dark, one more bright. Okay, now if we were to assign these n values like before, n equals 0, or m equals 0, m equals 1, m equals 2, m equals 3. Okay, m equals 1, m equals 2, m equals 3. And we'll call our dark ones n equals 1, n equals 2, n equals 3, n equals 1, n equals 2, n equals 3. Okay, so we've got enough that we've got our bright. We've got to our third antinodal line. Sorry, our third nodal line. There we go, I can read. So we've got 1, 2, 3, 4, 5, and 1 out there. Okay, it's kind of like a graph. Bright, dark, bright, dark. Okay, and it's telling us the distance between the third nodal lines on either side is 3.2 millimeters. And nodes are dark, n equals 3, so it's telling us this distance here from dark 3 is 3.2 millimeters. Okay, but we know we're doing calculations with only half, so we need to know that this distance here, 1.6 millimeters. Okay, so A. Okay, the wavelength of the wave. Lambda is our unknown. Okay, what equation do we know that we can use lambda from? We can get lambda, and we're talking about nodes. So let's look at our equations again from here. We're talking about dark parts, dark or quiet parts. So we do P equals n minus half lambda. All right. PD equals n minus 1/2 lambda. All right. So we're going to do this. We know n. We're going to find lambda. That's our final goal. But we don't know PD. Okay, how we're going to find PD? We're going to use, which I hope you did, PD equals dx over L. Okay, so let's go ahead and do that. D, 0.001 times x, 1.6. Oops. Let's do my units properly, my nolens. X equals 1.6 millimeters equals 0.0016 meters. Okay, that's really important. 0.0016 meters. Don't need the unit. Get rid of that. Okay. And then we're going to divide by our separation, which is just 1, which is really excellent for maths, which is really nice. Okay, and we're going to get a very, very small number, okay? 0.1234516 meters. Okay, that's our path difference, which is great, okay? So that's PD. PD, quite small. Now we can go ahead and use that equation. We can take this number over here, and we're going to place it up into that equation over there, okay? So we're going to say we want to find lambda, so PD equals, my bracket's in the wrong spot, I do apologize. Okay, PD equals n minus 1/2 lambda. So lambda equals PD divided by n minus 1/2. Okay, 0.0023456 n, which is 3, because we're at our third nodal line, minus 1/2. Okay, let's do that. Equals 6.4 times 10 to the negative 7, and we're getting a wavelength, so it's in meters. Okay, there we go. Tick. That's 3A. Now let's read again 3B. Describe the brightness. We know the fringe is this far from the central bright fringe. Okay, carry out calculations to justify our answer. Okay, when it says describe the brightness, what it's really asking is it bright or is it dark? Okay, so 3B. Is it bright or dark? Okay, and we know from the question x from the center is 1.3 millimeters. Okay, x equals 1.3 millimeters. Okay, now how are we going to know if it's bright or dark? Okay, is it bright or dark? Is n a whole number? This would be a PD equals n lambda, so it would be an antinode. Antinode. Is n 0.5 of a whole number, which would make it a node. Okay, so we want to figure out what's n. How close or how many multiples of the path difference go into the wavelength. Okay, because that's what we really want to know. So let's see if we can do this. All right, we know PD equals dx over L. That's great. We should find the path difference for this specific fringe. We don't know which one it is yet up here on our diagram. We just know it's going to be one of them or very nearby one of them at least. All right, so let's find the path difference for our new x value. We know d is still 0.001. We've got a new x value, 0.0013 meters, still divided by 1, our length. Oops. Okay, should be 0.12345513 meters. Okay, that's our path difference. Cool. Now, does this fit into wavelength easily? Okay, so we're going to take our wavelength of the light, lambda, down to here. All right, so what we want to look at is how do they compare to each other? All right, we can see that our wavelength is 6.4 times 10 to the negative 7, whereas our path difference for this new fringe is 1.3 times 10 to the negative 6. Okay, so they should be quite close together. So let's see if we can take 1.3, 0.123. Okay, if we take our PD and divide it by our wavelength, because it's smaller, that's the only reason I'm doing it that way around. Okay, path difference 0.1234513. We get 2.03. 2.03. Okay, so path difference equals 2.03 lambda. Okay, and this is almost a whole number. Okay, that should remind you of our equation, PD equals n lambda. Okay, which we use for antinodes, which are bright. Okay, they look very similar. N is almost a whole number, which means it's almost at the antinode. It's slightly off to the side, so it's not quite the brightest. It's a little bit dim because it's not quite at the peak antinode. Okay, it is very near an antinode. Okay, oops, almost maximum brightness. All right, almost. It's so close. All right, if that was 2, that would be maximum brightness. But it's very, 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 very close. All right, we will leave that there. Those are the answers. I hope that helped. Thank you for doing some work this week. Thank you for checking up on this, and enjoy your week.